Hey guys, thanks for tuning into CMTEQ channel in the series of tutorial on electrical power distribution. More specifically, this is a topic on two-wire distributor. If you are not familiar with the topic, please watch the previous tutorial on this series. In this tutorial number 6, we're going to solve yet another two-wire distributor problem, where the problem statement is that a two-core cable, basically a two-core cable, so that is a cable that only have two wires, right? That is 400 meter long, and its resistance is 0.04 ohm per 100 meter of a single conductor, right? This basically means, since it is a two-core cable, but the resistance per 100 meter of a single conductor is 0.04 ohm, so which means for a two-core, you have to double this value. There are loads of 6 amp, 80 amps, and 30 amps at distances of 100 meters, 150 meters, and 250 meters respectively from one end, right? If the cable is fed at 240 volt at each end, calculate the current in each section, the voltage across each load. Now the story here is that the last sentence here, if the cable is fed at 240 volt at each end, so this basically means we are having power fed into the circuit on both sides, okay, on both ends of the circuit. So having said that, we then need to find a way where we're going to calculate the current on each section and the voltage across each one of these loads. Now, the best approach to solve this type of problem is obviously you have to draw your network out. That way you're going to see your circuit clearly, okay, and it's going to make it much easier to solve it. So the first point here, we know that there are these loads of 60 amp, 80 amps, and 30 amps situated at these distances from what? From one end of the supply, right? Because we know that the circuit is fed from both ends. So here we go. We're going to just choose a 1 point, okay? So we just choose a 1 point here, okay? And from those points, we place our first load, okay? And this first load of ours is a load of 60 amps. So we're going to draw the 60 amps. Then we move from the 60 amp, right? And there is another load, and that load is said to be what? 80 amps, okay? So that's 80 amps. Then we move again from there. There is another load, and that load is 30 amps, right? 30 amps. Then we know that since this is fed from both ends, so there is going to be another supply from this side. But we know that it is a two-wire distributor, so we can then just put a second wire from our circuit. Now our circuit is coming along, okay? Now we can say that this point here is point A, right? And this is point B. And on this side, we will have point C and point D. Now these are both ends of the input, so which means we're going to have 240 volt DC being fed at this point here. And we're also going to have another 240 volt DC that is also fed from this side. So now we can complete our circuit by adding other critical information, such as the total distance of this cable is 400 meters, so which means our network here have a total length of 400 meters, right? So this is 400 meters, okay? And these loads here, they are situated at 100 meters. This particular one, okay, from one end, which is this end, since we chose to put a 60 amp from this side here. So basically here we should have 100 meters distance here, okay? And from there to this second load here, we should have another distance, and this is going to be 50 meters, because from A to this point here, we should have a total of 150 meters, right? Then this load here, the 30 amps load, is situated at 250 meters from this particular point here. So which means this distance here should be 100 meters. Right, now if all of this is 250 meters, but we know that the cable is supposed to be 400 meters, so that basically means this point here is going to be 150 meters. Now we can go ahead and name some of our node here. So we can say this is node E, and this is going to be node F. Then this is going to be node G, this is node H, and this is node I, and the last node here is going to be node J. Now before we can start finding the current in each section of the circuit, we first need to know our unknown current. Now assuming that at this point here, at this point we've got a particular current X, okay? So this is X is our current, okay? And we know that there is a current that is flowing here that is 60 amps. So which means this 60 amps here is being drawn from this X here. So that basically at this point we're going to have X minus 60, right? And when we get here, we know that there is another 80 amps that is being drawn from here. So which means the current at this point is going to be X minus 140. And the same will happen here since there is a current of 30 amps that is flowing at this IJ branch. So which means at this point here, there's going to be a current of X minus 170 amps of current. Correct. And this current, we don't know the direction. I'm just placing the direction as it's going this way. But remember, we are being fed from both ends. So which means there could be a current flowing this direction as well. But you have to note to the fact that both these potential, they are exactly the same. So which means they are actually going to be distribute the power to these branches equally from each one end of the section. Okay, now that we've got our circuit completely drawn and we've placed all the variables that we need to start solving, we then can move on to the first question here. But before we do so, please give this tutorial a thumbs up if you find it helpful at this point, and subscribe to CMTEQ channel so that you don't miss tutorial of this nature. Now the first question is the current in each section. So that is question number 1. But we know that we cannot find the current without knowing the resistance of the path that the current is taking. So according to our problem statement here, we know that this cable have a 0.04 ohm resistance per 100 meters. So which means for this section from A to E and F to B, we're going to say R sub AE to FB, it is going to be equal to 0.04 ohm, right, per 100 meters times 2 times 100 meters. Why 2? Because it is 2 wires, one wire and the second wire, so the positive and the negative wires, and this result is 0.08 ohm. So this is the resistance for that section. Now we move on to the next section. So that is R EG to HF, and the resistance on this section is 0.04 ohms, okay, over 100 meters times, okay, 2 times what? 50 meters. And this into the calculator give us a value of 0.04 ohm. Then the resistance for the next section, that is R GI to JH, and that resistance is 0.04 per 100 meters times 2 times 100 meters, and this gives us also a value of 0.08 ohm. Right, now one more resistance value here, and that is now the resistance for this section here, and that is R IC dj. And that is going to be equal to 0.04 ohm per 100 meters times 2 times 150 meters. And this gives us a value from the calculator of 0.12 ohm. Now from here, we know what is our problem. Our problem here is to find X, right? Because if we find X, we basically will know what are the current in each section. That's what the problem is. So, but how are we going to find it? Well, we're going to use Kirchhoff's first law. That is a law of conservation of energy. So that basically the sum of voltage drop across all of these sections must be equal to the difference between these two input voltages, right? So to apply that, we basically need the voltage drops. Since we know what the resistance are, we can basically calculate the voltage drop in each one of these sections. So the voltage drop on the first section is the current times its resistance. So that basically is equal to 0.08 times X, because the current on that section is X. Plus, now remember, this is a sum of all the voltage drops that must be equal to the difference between these two input voltages. So now the voltage drop on this section, so that is the resistance of that section, it is equal to 0.04, okay, times the current on that section, which is X minus 60. So it X minus 60 amps, plus the resistance on the next section, which is 0.08 times the current on that section, okay, which is equal to X minus 140 amps, plus the voltage drop on this last section. So that is equal to the resistance of that section. So that is 0.12, okay, times the current on this section, which is X minus 170 amps. Right, now this is equal to what? This is equal to the difference between these two voltages, the two input voltage. So that is VAB minus VCD. Now from here we can basically deduce a basic algebra here. So we're going to have 0.08 X plus 0.04 times X, so that is going to be 0.04 X, okay, plus or minus 0.04 times the 60 amps here, and we know that that's going to be minus 2.4 amps, plus 0.08 times X, that's 0.08 X, minus 0.08 times 140, and that is going to be equal to minus 11.2 amps, plus 0.12 times X, so that is 0.12 X, minus 0.12 times minus 170 amps, and that's going to be minus 20.4 amps. And this is equal to the difference between the two voltages. Now we know that the two voltages are what? 240 volt and 240 volt. So 240 volt minus 240 volt is equal to what? 0. Okay? So as simple as that. If one of these voltages were different, okay, we will get a different value here. And I tell you, if you find the current value, you add this up, this should verify. It should verify. If it does not verify, that basically means the Kirchhoff's first law of conservation of energy is actually not verified. So it has to verify unless you make a mistake. Now remember, these are the voltage drop on each one of the section. These are the voltage drop. These are the voltage drop. And this is a difference between the two voltage on the input. Now when we simplify this equation, we're going to find 0.32 X minus 34 amp is equal to 0. And from here, we can then deduce the value of x. So the value of x is going to be equal to 34 amps divided by 0,32. And this is going to be equal to 106,25 amp. So that's the value of x. Now to verify your equation, simply take the value of x here, which is 106.25 amps, and replace x value in this equation, and that should give you the value of 0. If it doesn't give you 0, that means somewhere either your resistance values or something is wrong. Now, since we now find the value of x, now it is very easy for us to deduce the current. Now we know that x is 106.25 amps. So that basically means the current in this section here, okay, which we call I A E to FB, all right? So that current is 106.25 amps. And then the current in the second section here, okay, so that is I EG to HF. So that current is X minus 60. So that basically 106.25 minus 60, okay, and that is equal to 46.25 amps. And then the current in the next section, okay, so that is I GI to JH, and that is equal to X minus 140. So that is 106.25 minus 140. Okay, now you can see that you're going to get a negative current, and that is minus 33.75 amps. And that is precisely because these two potentials are basically equal. So we're going to have this one pushing the current into this direction, while this one trying to push the same current in this direction. Equal currents. Right, now we're going to now have the current on the last section, and that is IC to DJ, and that is going to be X minus 170. So that's 106.25 minus 170, okay, and that gives us a current of minus 63.75 amps. So these are the current on each one of these sections. Now we move on to the second question, okay, so this is question 2. Question 2 is a voltage across each load. Now this is very simple. Now regardless of which direction you calculate your voltage on each one of these sections, you still going to get exactly the same voltage at each one of these points, okay, because your circuit is basically verifying. Now in order to find the voltage at point EF here, okay, so we're going to say V EF is basically equal to the 240 volt, right? So that is 240 minus what the voltage drop at this point here. Now the voltage drop at this point here is basically the current here times the resistance, okay? So that is 0.08 times the current on that section, okay, we know it's X, so that's 106.25, okay, and when you compute this, you get a value of 231.5 volt, okay. And then when you move to the next section here, section GH, remember you no longer seeing 240, you are now seeing the voltage coming from this section, which is 231, that need to drop some voltage here, okay. So then that's going to be VGH is equal to 231.5 minus the voltage drop on this section, knowing the resistance is equal to 0.04 times the current on that section. We know what's the current on that section. We have already calculated that current, and that is basically equal to 46.25, okay. So this is 46.25 0.25. And when you compute this in the calculator, you find a value of 229.65 volt. Okay? Now for the voltage drop at point IJ. Now remember, all these other voltages that we just calculated, we will exactly get the same value if we start calculating from those point AB or from point CD. They will be exactly the same voltage because the circuit will have to verify. Now, we're going to first calculate the voltage across IJ by using the voltage drop across GH, so which means we are flowing from AB to this end. And then we're going to also calculate the voltage across IJ by using this voltage at this input point here, 240 volt. And we will prove that it will be exactly the same value. So for that, we're going to say VIJ is equal to what? 229.65, because that is a voltage drop at GH, right? Minus the resistance on this section. What's the resistance on this section? We know that the resistance on that section is 0.08 ohm, 0.08, times the current, okay, on that section. That current is X minus 140, and X minus 140 is basically negative 33.75 amps. So we're going to have negative 33.75 amp of current. Right now, this is the current pushing from this direction into this voltage source. So which means this current is negative because it's going the opposite direction with the same current that is actually trying to go the other direction. So it's negative. Then computing this, we're going to get a value of 232.35 volt. Now, we're now going to calculate the same voltage drop across this point, but this time by using the voltage from this other end of the input. So we're going to say V is basically going to be 240 volt, right? Minus the voltage drop on this section now. Now the voltage drop on this section, we know that it is equal to its resistance and the current. The resistance of that section is 0.12, okay? Times the current on this section, it's X minus 170, so that is going to be 63.75. Now, we cannot put negative 63.75 because the current is flowing from the positive direction. So basically, it's flowing from the positive end of the input voltage to the side. Unlike when the current was flowing from this side to this side, then it will be flowing from the positive to the negative. So now it's flowing from the negative to the positive side. So which means it is a positive current. So we're going to then write 63.75. And when we compute this, we are surely going to get 232.35 volt. And it does exactly verify. This is it for this tutorial, guys. So if you found it useful, please give it a thumbs up and subscribe to CMTEQ channel. Stay tuned for more tutorial like this in the upcoming tutorial. If you have any comment, question, please drop it in the comment box and I will attend to it as soon as possible. Until next time, stay tuned. Cheers.